In the previous video, in this module, we have built a framework for learning policies based on Q-learning. We have also pointed out some limitations of this approach for robotics and autonomous vehicles along the way. Let's summarize them now. First, it can be very unsafe to let a robot learn from its mistakes in the real world, particularly in an application like self-driving cars. Next, the RL paradigm assumes that the environment is providing the reward signal to the agent, but it's unclear how this might happen in a real-world robotic setting. Also, training deep RL agents tends to take a lot of trials, on the order of millions of trials even to solve relatively simple problems. This is problematic on real hardware since it can be expensive to operate and maintain. Finally, the real world imposes real-time constraints. It's not always the case that a robot can sit and take a long time to update its Q function estimate while other things are still going on in the real world. An appealing option that would solve basically all of these problems would be to let the agent train in a simulation environment and learn a policy that can then be deployed in the real world. This problem is sometimes referred to as sim to real. The major issue is that a simulation environment will never be exactly like the real world. Let's think about the simulation environment and the real world and think about how different errors might get introduced. A robotic system comprises an agent and an environment. The environment is controlled through commands generated by the agent and sent to actuators, and is observed by the agent through observations generated by sensors. Similarly, a simulation contains an agent and an environment model. Instead of a real actuator, the control commands are issued to a dynamic simulation. And instead of real sensors, the observations are generated by a renderer. The performance of the agent is determined by how well it does according to some metrics that define the specific task that it is set out to achieve. In some cases, like reinforcement learning, this performance can be fed back to the agent to help it learn over time. If we analyze this mirrored setup a little more closely, we can see that a so-called reality gap or discrepancy between a simulation and the real world can be generated at several stages. Specifically, the dynamics model, the environment model, or rendering could all be inexact. Moreover, one would reasonably expect these reality gaps to compound, where upstream errors are exacerbated downstream. So what if we want to formally quantify how good or useful our simulator is? Or conversely, how big this reality gap is? A naive approach might be to take a sequence of control commands and apply them to both the actuation on the real robot and the dynamic simulation in the simulator. We can then take the observations at the output and simply compare them, for example, with a pixel-wise norm for the case of a stream of images. The issue is that it's not clear where the real source of the discrepancy is coming from, which makes it difficult to build a model to overcome it. We can see right away that predicting or accounting for the difference between the simulation and the real world in some meaningful way is going to be challenging. Note again that the root of the problem from a deep learning perspective is that we have again violated the IID assumption, since the data sampled from the real world where the robot is deployed does not come from the same distribution as the simulated data where the robot was trained. In the literature, there are at least two general approaches to overcome this problem. The first idea, called domain adversarial transfer, is to use data that you might have from the real world that was collected outside of your RL training loop. The objective then is to use the data and the simulator to learn a function that maps from one domain to the other. We'll call that function G. If we could build such a function, then when we deploy our robot in the real world, we can pass our sensor data through this function to make the agent think that it's still in the simulator. One way to build this function would be to have exactly matching images from the two domains and then label them and train a classifier. This would be a bit cumbersome though. Instead, we can use a generative adversarial network, or GAN, to help do the job for us. In the GAN setup, we have a function or generator that consumes real images and generates fake simulated images. We also have actual simulated images. Then there is a discriminator whose job is to try to discern whether the images it sees are true simulated images or the fake ones generated by the generator. The generator is incentivized to try to fool the discriminator, and in so doing learns to generate images that look like they came from the simulator. At the end of training, This generator is exactly the function that we need to apply to our real images when we deploy the real robot. Another class of approaches attempts to directly align the two data distributions so that the agent can automatically transfer from the simulator to the real world. The problem is that there are many parameters in the real world that we don't know exactly how to set in the simulator, such as lighting parameters or dynamics coefficients, and many others. To overcome this, we can randomize over these parameters that we aren't sure of during the training in the simulator, an idea referred to as domain randomization. The hope is that when the agent is deployed in the real environment, it will perceive the real environment as just another randomized instance of what it was exposed to in the simulator. Domain randomization and domain adversarial transfer work to some extent, but it's important to emphasize that this is still a very active area of research, with new papers getting published improving these methods every day. This concludes the overview module on reinforcement learning. We have seen that we can formulate this problem as a Markov decision process and solve it with an approach like deep Q learning, which extends policy iteration to high-dimensional spaces with deep neural networks. We have also seen that there are important special considerations for autonomous vehicles, and we have introduced approaches like domain adversarial transfer and domain randomization for training and simulation and transferring an agent to the real robot hardware to overcome these challenges.